Hey guys, Mitch back at it with another weekly tech tip video. Today is part 2 of our virtual data optimizer video. Last week I gave you an in-depth kind of run through of what VDO is, some use cases for it. And so this week I'm going to bring you over to my desk and we're going to sit down and we're going to set it up and I'll show you how you can use VDO yourself at home. And then I have a really cool experiment planned, so you definitely want to stay tuned for that. Alright, so welcome to today's video tutorial tech tip. So if you haven't watched my last week's video, you definitely want to pause this one and go check it out because it's going to give you all the context you will need to understand VDO, what its purpose is, and kind of what we're doing here today. So first I'm just going to show you how to install VDO. And so I'm running CentOS here, so if you take a look, there we go. So I'm running a 7.6 version of CentOS, and I believe I'm on the 3.10 kernel. But any version of CentOS should be fine. Any version of 7 or above, actually. So VDO itself is made up of a kernel module, KVDO, and then the command line tool that's used to interface with it, which is VDO. So to install everything on a CentOS installation, it's very simple because it's already included into the repos that come standard. So what you're going to do is you're going to run a yum install kmod VDO and VDO. And I already have it installed, but that's all it would take to do. And once that installs, you're ready to get started. So we're going to set up a live demonstration of VDO in action here, and this experiment is actually really cool and can show you just how great VDO can work in the right circumstances. So I actually got this idea from Red Hat and a demonstration they did a while back, and I'm going to do a little different, but this is really cool. So let's just get started. So as we go through this, I'm going to explain and talk about VDO as we get the demonstration going. But first, let's talk about what I'm going to show off. So if you take a look here, I have over 20 versions of the Linux source code. And these are actually compressed into tar files. So we're going to decompress each one of these straight into a VDO backed file system as well as a non-VDO backed file system. And so while each version of the kernel source code files are going to have a little bit of differences because they're obviously different versions each time, there's going to be a massive amount of duplicate data here going from one to the next. And then also, since mostly it's all text files, they're also very susceptible to compression. So we're going to pretty much see what it looks like if you have the absolute best conditions to use VDO and just how much space you can save with both compression and deduplication on the same file system. So to get started, let's just take a look here. I have 2 block devices created and they're both 25 gigs in size, and so one is going to be created with VDO and then one is going to be just a standard XFS file system. Alright, so first things first is I'm going to create a VDO block device out of one of these 2 block devices that I have. So essentially what VDO does is you take a block device that you want to use for your dedupe and for VDO, and you plug it into VDO, and then it creates its own VDO backed block device that you can then put a file system on. So let's just do that. So we'll go VDO create name. Let's just call it VDO test. VDO test. And then we're going to give it a device. Dev. Let's go SDB. And then you're going to want to give it a logical size. So as you can see here, they're 25 gig size right now. So this is where knowing your data set is really going to come in handy when sizing your logical size. Since we know our workload is the Linux source code and it's a lot of data that's going to be dedupable and compressible, since they are text files, we're going to be using a 10:1 logical size. So if you want to know more about this and you want to have some tips on how to size your VDO disk, check out the Red Hat docs. I'll actually leave a link in the description. But just for a rule of thumb, if you're planning on using it to host VMs or containers or something like that, Red Hat actually recommends doing a 10:1 logical to physical. And then if you're using object storage, something like Ceph for example, they recommend a 3:1. So as I said, we're going to be doing a 10:1. So let's go VDO logical size 250G. There we go. We've created our VDO and it's ready to go. So there's also a command that's video stats that you can take a look at the video you're using. So as you can see, we have some blocks used here, and that's because video does have some overhead. It seems rather large here because we're only using a 25 gig disk, but it really doesn't grow that much. Like if you're using a multiple terabyte video disk, video really just uses pretty much the exact same amount as it's saving here. So as you can see, we're not saving any space as of yet because we haven't done anything. Alright, so the next step is to create a file system on this. So we're going to be using XFS for our file systems. So let's go makefs.xfs-k, and we're using -k so it won't attempt to discard any of the blocks when making a file system. Okay, and now we're going to go dev, and as you can see, the new video back device is at a different location than just SDB was. So we're going to do mapper. Alright, so the next step is to create a mount point that we're going to mount this video at. So let's just make it very simple. Mount video test. And while we're here, we might as well make one for the non-video. Let's call it mount non-video. And now let's create a file system on the other block device that's not going to have video underneath. So mkfs.xfs/dev sdc. There we go. Now we're going to mount our two file systems. Okay, so we have our video mounted, and now we're going to mount our non-video. There we go. Let's take a look-see. As you can see, our dev mapper video test is presenting as 250 gigabytes, whereas our non-video is just presenting as its actual size. And then again, we can do a video stats to get a look at our video block device. And as we can see, we're at 99% saving now because we don't have any data on the device as of yet. Alright, so before we continue with the actual demonstration and the test, I first wanted to touch on video itself and just go through some of the features of it. So if we take a look, video-h, you can actually see some of the things you can do right away. So obviously it's great that you can actually grow it in size logically and physically after the first creation. So that's great, and it's also great that you can enable and disable certain parts of it. So if you only want to enable compression and not deduplication, you can do that here as well. And then there's different write policies you can use as well, and this can all be found in the Red Hat docs, all the differences you can use. And then there's one other point I wanted to show as well. So as you can see here, there's quite a few different things that we can look at here, and it's setting different thread counts, CPU thread counts, logical size, read cache size, and there's also write caching as well. So what I'm going to say is, last week I discussed in the video is that video can be computationally expensive, and that's very true, and you will see a read-write penalty for sure, but it's up to you to see if it's worth it for your use case and in your environment. But what I'm going to leave you with here is video kernel driver itself is very multi-threaded by default, so they built it very robust in that manner, and it's in order to improve performance by as much as possible. They allow you to really try to finely granularly tune your performance the way you'd like to. So there's a lot of tunables in here that you can interact with to improve performance via the logical and physical CPU and I/O work. They can be spread across into a multi-threaded workload, and this is, again, can all be tuned during initial configuration or after the fact as well, as long as you restart your video device after you're done. So unfortunately, performance tuning is a little out of the scope of today's video, but I did just want to touch on that and show you that all this is possible once you get it up and running. There is a lot that you can play with to try to improve performance from the base performance that you may be getting right right out of the gate. Okay, so with that being said, let's clear this here and let's continue on. So I'm gonna move over to this terminal and I'm gonna move into the kernel's directory as well. So let's list all the files here. So I think there's 22 if I'm not mistaken. Let's take a look. Yes, okay, we have 22 different versions here. And what we're going to do is we're going to just run a command that loops and untar and completely decompresses and untars the entire, every single file in this directory into both our video mount point and our non-video mount point. So let's, alright, so we may be able to actually watch this increasing its size while we do it. So let's try this out actually. So let's just try to run a watch video stats so we can see this in real time as it goes. So first I'm going to put that right there. Now the command that I will run. So I'm going to do for_i and then we're going to do ls do. So we're going to tar. And we're going to go into video first, and then for the next one we'll do the non-video back device. Alright, so F. If you want to know what I'm doing here, you can actually go into the tar manual and it'll tell you what each of these do, but essentially it's being verbose and unzipping, and so yeah, you can go and just take a look if you're interested in that. And now we're going to be done. So what this is going to do essentially is it's going to list out every one of these files, and as it does that, it's going to loop through and untar and decompress each one of these into our video backed file system. So let's try here. So there it goes. So now we can watch it happen, and in real time we can see the space, and this is actually going to run for some time. So most likely what I'm going to do is let it run and then we'll come back once it's finished. And actually while this is happening, let's just do it again and we can get both of them going at once. So let's also untar into the non-video. So let's take our for_i in ls do c mount non-video is the name of our other file system, zxvf, we go $i, and done. So this is going to do the exact same thing on our non-video backed file system. And now we can just let them run, and when we come back we'll see just how much space we saved on our video and just how much space it actually takes up if you weren't to use any decompression or deduplication. And actually, while it's running, if we want to view the non-video backed device and how that's doing, we can actually pull up another terminal. Let's just watch mount video, non-video, and oh, my bad. Actually, it's a df mount non-video. Let's take a look here. Alright, so now we can watch this in action as well, and we can see just how much is used and how much is available. And let's just let it continue from here, and we'll come back when it's done. Okay, and we're back, and it looks like it has finished. So this isn't very helpful for us because it's actually not very easy to read, but let's just try this. Video stats human readable to make it a little easier for us. Okay, so as we can see here on the non-video backed file system, we use 19 gigabytes and we have 6.6 available back to us. Now on the video, we only use 6.9 gigabytes, which is quite good amount of savings here. and we still have 18.1 gig. So our saving percentage, as it says here, is 79%. That's really not bad at all, especially if you have a use case that really is conducive to this type of thing. Like for example, I mentioned it in the last video, but if you had to send a lot of data up to the cloud for disaster recovery purposes, if you deduped it and compressed it with something like this first, that really could save you a lot of time and money. Alright guys, so thanks for watching. Hope you enjoyed that. If you have any questions or comments, be sure to leave it down below and we'll get back to you as soon as possible. Also, if you're not subscribed, get subscribed and give us a like. It really helps. Thanks.